Welcome, everyone, to this explainer. Look, if you're up late studying for an exam, grinding through a tough engineering concept, or honestly, just feeling a little overwhelmed today, I want to invite you to just take a deep breath. Let's drop the stress for a few minutes. Today, we're going to gently unpack a topic that, sure, sounds incredibly industrial, but is actually quite natural. We're talking about the chemistry of water's impurities, specifically focusing on this thing called sludge. We aren't going to treat this like some stressful, high-stakes problem you have to memorize. Instead, we're just going to take a peaceful little journey through how water works.
Section 1. The baggage water carries.
Water covers almost 75% of our planet. It's the Earth's ultimate universal traveler. It's actually the only known substance that naturally exists as a gas, a liquid, and a solid right within our normal everyday temperatures. And as it travels and flows over the surface, it picks up souvenirs. It gathers up dissolved particles of soil, minerals, sometimes chemical wastes, and organic matter. Which kind of leads us to a really interesting question. What actually happens when our universal traveler simply carries too much baggage?
Well, we hear a word like impurities, and we instantly think of failures, right? Or contamination. But natural water carries these impurities in dissolved, suspended, and colloidal forms, literally just because it's doing its job as a solvent. These solids aren't mistakes. They're just part of water's journey, whether that water is flowing in a beautiful natural stream or rushing through a massive industrial pipe. Eventually, water just needs to put that baggage down.
And when it finally does put that baggage down, under the right conditions, we get sludge. Now, I know sludge sounds kind of gross, but listen to how it's defined in engineering chemistry. It's a loose, silky precipitate suspended in water. Notice those words, loose and silky. Even in a dense, heavy textbook, the language used to describe this reaction is surprisingly calming. It's not some rigid, catastrophic failure. It's just a soft, yielding gathering of particles that have gently fallen out of the solution.
Section 2. Trouble in the boiler.
Okay, so let's see how this builds up in a real-world application. We're going to look at an industrial setting, specifically a boiler, where intense heat forces the water to finally drop its luggage. In factories, water is continuously heated under super high pressure to generate steam. As that water evaporates and leaves the boiler as pure steam, the dissolved salts left behind start to concentrate. Eventually, they hit a saturation point. They just can't stay dissolved anymore. So, they gracefully precipitate out. The water leaves, and the solid baggage has nowhere to go but down.
And the way those solids settle out happens in two very different ways. First, you've got our friend sludge, that loose, free-floating precipitate just hanging out suspended in the water. It usually forms in the comparatively cooler portions of the boiler. But then you have something totally different, which is scale. Scale is this hard, stubborn coating that literally bakes directly onto the inner wall of the boiler, right where the heat is at its most intense.
Section 3. Sludge versus scale.
Let's gently disassemble the differences here, because understanding this is absolutely crucial for keeping these massive systems running safely. Sludge is formed by substances that actually dissolve better in hot water than in cold water, things like magnesium chloride. So they settle in the cooler areas, staying soft and loose. And because they're loose, we can easily clear them out using a routine called a blowdown operation. Scale, on the flip side, is formed by stubborn salts like calcium sulfate. As the boiler gets hotter, these salts become less soluble, baking into a rigid crust that is incredibly difficult to scrub away.
Now, even though sludge is definitely the softer, gentler issue compared to explosive scale, it still needs mindful management. If we don't clear it away, it just sits there, settling in slow circulation areas. It can quietly choke up pipe connections, and because it's a terrible conductor of heat, it wastes valuable fuel and drags down the boiler's overall efficiency. It's a really good reminder that even soft, manageable problems need to be routinely cleared out before they build up.
Section 4. The wastewater gather.
We've seen how sludge acts in a closed boiler, but let's step outside for a second. We're going to look at municipal wastewater, where sludge takes on a completely different and honestly surprisingly beautiful role. When wastewater from our cities hits a treatment plant, it goes through this very methodical, calming process. First up is primary treatment, which is basically sedimentation. The water just stands undisturbed in these giant tanks. The heavy impurities naturally settle out at the bottom as, you guessed it, sludge. This clears the way for secondary treatment, where helpful little aerobic microbes break down the remaining organics. Finally, tertiary treatment handles the superfine filtration and disinfection. But the real heavy lifting? That's done right at the start by simply letting things settle.
And the sheer volume of sludge generated in that primary step is huge. But let's completely reframe how we view it. This sewage sludge contains soil particles and incredibly rich organic matter. It's not just waste, it's a gathering of nutrients. When it gets stabilized and dried out in the sun and fresh air, the bad smell fades away and it transforms into a highly effective fertilizer. The baggage the water was carrying goes right back out to heal and feed the earth.
Now, to make sure this wastewater is actually safe to release, engineers measure two specific things: biological oxygen demand, or BOD, and chemical oxygen demand, or COD. Honestly, you can just think of these as simple measurements of how much breath the water needs. BOD measures how much oxygen those helpful bacteria need to naturally break down the organic stuff. COD measures the total oxygen needed to oxidize absolutely everything, organic and inorganic. By keeping an eye on the water's breath, we know exactly when it's healthy enough to return to nature.
Section 5. Finding the balance.
So what does this all mean? The absolute crucial takeaway here is how we manage all this baggage to find a peaceful balance. In an industrial boiler, we restore balance by softening the feed water to near zero hardness before it even gets hot, basically preventing the problem before it starts. We use those routine blowdown operations we talked about, just gently drawing off a little bit of the concentrated water to let the sludge out. And in our city water supplies, we use simple screening and gentle aeration, exposing the water to oxygen to release trapped gases. It's these simple, routine, low-pressure actions that keep massive systems perfectly in balance.
As we wrap up, I want to leave you with this incredibly soothing thought straight from the textbook regarding water recycling. Natural purification by slow percolation of the wastewater into the soil, which eventually recharges the groundwater with clean water. It's like a giant, natural reset button. Just as the Earth patiently and slowly filters water to replenish itself, we too can take the time to clear out our own mental sludge. So think about it. If massive industrial boilers and entire city infrastructures need routine blowdowns to clear their buildup and function, what small, daily routine might you need to implement to clear yours? Thanks so much for hanging out with me for this explainer, and I really hope you carry this calm clarity into whatever you're tackling next.